Hi everyone, in this video on geometric sequences, we're going to be learning how to find the first term in the sequence which is greater than some given or stated value. And when studying geometric sequences, this exercise is an absolute must-know-how. So let's go ahead. On the screen here you can see our must-know exercise, and we're told a geometric sequence has first term 5.7 and common ratio 1.2. We're then told find the least value of n such that the general term, u sub n, is greater than 1000. Now, if you're up for it, before watching the rest of this video, go ahead and press pause and try solving this on your own. Either way though, let's get started. Let's see, I'll start by moving this question to the side, like so. And as I always do, I'll go ahead and write SOL here for solution. Now, what I always like to do is quickly summarize the information that's given to me in the question. So again, here we're told that we're dealing with a geometric sequence whose first term is 5.7, and we'll definitely want to make a note of that. And in fact, I'll even label it like this. The first term, u sub 1, is equal to 5.7, and whose common ratio, let's see, common ratio is equal to 1.2. So in a similar way, I'll make a note of that. The common ratio r is equal to 1.2. The next thing I make a note of is the goal, or our target. And in this case, we need to find the least value of n, so the smallest value of n, such that the general term u sub n is greater than 1000. And so another way of putting all of that is we're looking for the first term in this geometric sequence which is greater than 1000, which is the same thing as figuring out which value of n leads to the general term, or nth term, being greater than 1000. There we go, and I'll go ahead and box that. That's our target. We're going to have to solve this inequality. Now here's the whole idea. Since we know that we're dealing with a geometric sequence, whose first term and common ratio are known, and since we need to figure out the first term in the sequence which is greater than 1000, that strongly suggests that we're going to have to make use of the formula for the general term, or nth term, of a geometric sequence. Remember, that's the formula which states that the nth term, or general term, which is u sub n, is equal to the sequence's first term, u sub 1, times its common ratio r, which is raised to the power of n minus 1. And I'll go ahead and box that formula. There we go. Now I'll also point out that if ever you are an IB mathematics student, then this formula will be in your formula booklet. But I'll also say, whether you're an IB mathematics student or not, when studying geometric sequences, this formula really should be known. That being said, I carry on. If I quickly make a copy of this formula, and I'll do so down here, so that was the nth term of the sequence, which is equal to its first term, u sub 1, times its common ratio raised to the power of n minus 1. And if I make note of the fact that the first term, u sub 1, is 5.7, and the common ratio r is 1.2, then this formula for the nth term becomes u sub n equals to 5.7 times 1.2 raised to the power of n minus 1. And as such, that's the formula for this geometric sequence's nth term, or general term. Now remember, we're trying to figure out the least value of n such that the general term, so this thing here, is greater than 1000. In other words, we need to solve u sub n, the general term, is greater than 1000. But now, since we know that the expression for u sub n is 5.7 times 1.2 raised to the power of n minus 1, this inequality turns into 5.7 times 1.2 raised to the power of n minus 1, which is greater than 1000. And at this stage, I'll go ahead and box that inequality. There we go. Solving this inequality will lead us to the value of n that we need to find. Indeed, solving this inequality will tell us the smallest value n can be such that this expression is greater than 1000. And to solve this inequality, there are two methods really. One involves using the graphical calculator, which is the one we're going to start with, and the other involves using logarithms. So let's go ahead and see how it's done with the calculator. Now for that, on my exam paper, I'd go ahead and write with GDC, which means graphical display calculator, we're going to plot a function, and I'll just say plot f of x. And the function we're going to plot is the function that we'll define using the expression for the nth term we have here, which is the same thing as what we see on the left-hand side of this inequality. Indeed, mimicking this expression for the nth term of our sequence, we can define the function which will be 5.7 times 1.2 raised to the power of x minus 1. Careful, here I'm writing x minus 1 on the exponent, not n minus 1. And now with that in mind, if I move over to my calculator, which you can see on the screen here, I'll go ahead and move to the graph section, which I do by clicking on this tab in the upper left-hand corner, right here, and I'll plot my function. So that's 5.7 times 1.2 raised to the power of x minus 1. And I'm happy with everything I've typed there, so I click on enter. And now here's the thing. I'm not even going to look at the curve I've just plotted. All I'll make sure of is that I entered the function's equation properly. And looking at the graph's label I can see on the screen here, it's indeed 5.7 times 1.2 raised to the power of x minus 1, which is exactly what we had written here. In other words, I'm happy with what I've entered on the calculator. Now that that's done though, I need to get to the table of values on this calculator. And this calculator is the TI Nspire CX, but regardless of the calculator you use, the method will be similar. Here though, to find the table of values, I go ahead and click on Menu, followed by the 7th option, Table. And I can see there's only one real option to choose from here, and that's Split Screen Table, so I click on that. Now I can see that my screen has been split in two. On the left-hand side I have the curve, or the graph, and on the right-hand side I have a table of values. And in this table of values, the first column represents the various values of x. In the second column, though, it has the values of f of x, this entire function. So in this context, the values we see for f of x are in fact the values of the terms of our geometric sequence. So when x equals to 1, that would represent the first term of our sequence, which is 5.7. Which comes as no surprise, we were told that the first term is 5.7. The second term, which is 6.84, is exactly what we'd get if we multiply 5.7 by the common ratio 1.2. And so thanks to the two columns we have in this table of values, we can effectively find any term we want in our geometric sequence. So for instance, let's say I wanted to find the 6th term, then I would go down to the value x equals to 6, and I could see right away that the term in the sequence would be 14.183424. And as such, we could carry on forever this way. But remember, we're trying to figure out the first term which is greater than 1000. And all we have to do for that is scroll down in this table of values until we reach a value in the second column which is greater than 1000. So let's go ahead. If I scroll down here, there we go, I'm at 35, I keep on going, 50, 60, 73, and so on. And I'll keep on going until I reach the value greater than 1000. There we go, we missed it there. It's right here. We can see that when x is equal to 29, the 29th term is equal to 939.614575457. We can see that at the bottom of the screen there. And we can see that when x equals to 30, the 30th term in the sequence is equal to 1127.537, and so on and so forth. And so writing those two values on our exam paper, we could go ahead and state that the 29th term, u sub 29, there we go, is equal to 939.6, and the 30th term, u sub 30, is equal to 1127.5. And so what that shows us is that when n is equal to 29, it leads to the 29th term of the sequence, which is 939.6, but when n is equal to 30, it leads to the 30th term of the sequence, which is 1127.5. In other words, the 30th term of the sequence is the first one which is greater than 1000. And all the terms that follow in the sequence, so the 31st, 32nd, 33rd, and so on and so forth, will all be greater than this value. And that's because the common ratio is greater than 1. So this term is definitely the first one to be greater than 1000. And so finally, to answer this question properly, we could go ahead and state that for the general term u sub n to be greater than 1000, we need to have n greater than or equal to 30. And so consequently, the least value of n such that the general term is greater than 1,000 would be the first value of n for which the term in the sequence is greater than 1,000, which we've just seen is the 30th term. In other words, n is equal to 30. That's the least or smallest value of n such that this general term is greater than 1,000. And as such, we're done. We've fully answered this question. And I should say, if we write all of this in the exam paper, we'll get full marks for this question. And so that's how we can solve this question with our calculator. And if that's all you were after, you can stop watching this video now. But if ever you're interested in seeing how we can solve this with logarithms, let's see how we can do that. And in fact, maybe I'll make it clear here. This solution here is with the graphical display calculator. And now on the right-hand side here, I'll say with logarithms. And just as I did at the bottom there, I'll go ahead and box that. There we go. Okay, now if we're solving this with logarithms, all our working and reasoning up until this inequality would be identical. In other words, we'd still be faced with this inequality to solve. 5.7 times 1.2 raised to the power of n minus 1 is greater than 1,000. Now to solve this inequality, the whole idea is to isolate this 1.2 raised to the power of n minus 1, since that's the term containing the unknown we want, which remember is n. And since on the left-hand side, this 1.2 raised to the power of n minus 1 is being multiplied by 5.7, we can get rid of that 5.7 by dividing both sides of the inequality by 5.7. So I write that here. And so this inequality becomes 1.2 raised to the power of n minus 1, which is greater than 1,000 divided by 5.7. Notice here that I'm not going to figure out what this is equal to with my calculator because I don't want to insert any rounding in my work. The next thing we need to do is to get the unknown n away from that exponent. And that's where the logarithms come into play. And so what I'll write here is I'll just say apply logarithms, or even apply logs. And so here's the whole idea. I'll go ahead and use the natural logarithm, which is ln, but you could use log base 10. It would make no difference whatsoever in the final answer. And so here I'll write on the left-hand side ln of the entire left-hand side, 1.2 raised to the power of n minus 1, which must be greater than ln of the right-hand side. So that's 1,000 over 5.7. Now, using our laws of logarithms, this power of n minus 1 will come out as a factor on the left-hand side. In other words, this turns into, in parentheses, n minus 1 times ln of 1.2, and that's greater than ln of 1,000 over 5.7. Now remember, we need to figure out what n is, and so to do that, let's get rid of this ln of 1.2 on the left-hand side, which is multiplying this pair of parentheses. And so to do that, I divide the left-hand side by ln of 1.2, and I do the same on the right-hand side as well, ln of 1.2. We're nearly there. This becomes, on the left-hand side, n minus 1, which is greater than the right-hand side, which is now ln of 1,000 over 5.7, and all of that's divided by ln of 1.2. Finally, I'll get rid of this 1 that's being subtracted from the left-hand side, which I do by adding 1 to both sides of this inequality. And so we find that n has to be greater than ln of 1,000 over 5.7, and that's divided by ln of 1.2, with a plus 1 at the end here. And now I move over to my calculator and I calculate the right-hand side that we see here. So let's see, I'll go back to my calculator, which you can see on the screen here. And so I type ln of, in parentheses, 1,000 divided by 5.7, and that's divided by ln of 1.2. I exit all of that and I add 1 to the end. There we go. I'm happy with what I typed, and so I click on Enter. There we go. We can see that n needs to be greater than, if I round it a bit, needs to be greater than 29.3. But remember, this n here has to be a whole number. Indeed, there's no such thing as the 29.3rd term in our sequence. So instead, we look for the first integer, or whole number, which is greater than 29.3. And of course, that's 30. So thanks to this result, we can go ahead and state that n has to be greater than or equal to 30. And just as we had written with our calculator over here, since we know that provided n is greater than or equal to 30, the general term of our sequence will be greater than 1,000, that tells us that the least value of n such that the general term is greater than 1,000 will be 30. So we would state our final answer as n equals to 30. That's the least or smallest value of n such that the nth term of the sequence is greater than 1,000. And so again, I'll go ahead and box that result. There we go. And there we have it. That's how we can solve this must-know exercise on geometric sequences using either your graphical calculator or logarithms. And there we go, everyone. I really hope that helped, and if it did, please hit like on this video, drop a comment down below, and even subscribe to this channel to help get this video to as many students as possible. All that being said and done, that's it for this tutorial.